Hello and welcome to our MIU today. My name is Maximilian Reimann and I will guide you through our event today. Before we start with today's presentation, please note that this session will be recorded. For this reason, we would like to ask you to turn off your camera and microphone. Questions about the topic are welcome via the chat function and will be asked to the speaker at the end of the event. And this brings us already to today's presentation. I'm pleased to welcome my valued colleague, Ms. Shandozi Bhattacharya. Shandozi has a master's degree in data engineering and several years of professional experience as a systems engineer and data scientist. We're looking forward to the presentation with the topic AI-based delay estimation for freight trains. Shandozi, the stage is yours.
Thank you, Max, for the introduction. And good afternoon, everyone. My topic today is AI-based delay estimation for freight trains. And as we know that trains are quite important for the operations in the maritime industry because they are efficient, cost-effective, and environment-friendly. And managing the arrival of trains is quite a challenging task for the inland terminals, and it would be very useful for them to have an early information about the arrival, the estimated arrival times. And that brings me to the motivation of our idea. So ETA forecasts would have multiple benefits, like it would help the terminals to plan their resources like staff, equipment, and storage areas efficiently. Then this timely knowledge of changes in ETA could be communicated to their customers, which are the truckers who come to the terminal to pick up or drop off containers, and this would increase their service quality. And finally, it would optimize the logistic processes like coordination of loading and unloading activities, storage, and transfer between different modes of transport. The goal of our project is to develop a model that would predict the arrival time of freight trains at the destination and compare them with a chosen baseline method. The model would consider historical delays, geographical data, and meteorological parameters. It observes the data from previous stations and is capable of predicting delays for subsequent stations. Also, the ETA would be updated periodically. Such kind of forecast would be very useful for container terminals, logistic companies, and even for railway companies. So for our topic, an LSTM model was chosen, which stands for Long Short-Term Memory Model. And before I explain LSTM models, maybe I can explain recurrent neural networks a bit. So the recurrent neural networks, they are very popular for sequence prediction tasks. So they take this XT as an input and produce HT as an output at the current time step. And the output is again fed back to the model. And this continues in a loop. So because of this, it makes the RNN suitable for remembering historical information. And based on that, it can make the predictions. But there is one shortcoming of RNNs, which is it can only remember very recent information, and it's not very suitable to consider the information that's way back in the past. And that is that's why we have LSTMs, which covers this shortcoming. So the LSTMs, they operate very similar to RNNs, with the only additional change that it has something called cell state. And the cell state is responsible for carrying only useful information from way back in the past and throughout the end. This is capable of filtering what information should be carried forward and what should be discarded at the moment. An example would help us understand the difference better. For example, in this sentence, the clouds are in the blank. RNN would successfully predict the missing word. But if there is a paragraph, then it would be difficult for RNNs to predict. For example, in the sentence that I grew up in France and blah, 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 and I speak fluent, and LSTMs would correctly predict the word. So LSTMs have certain advantages due because of which it was chosen for our task. Like it could automatically learn the underlying patterns in sequential data. It can capture spatial space and time related relationships. It can maintain both short term and long term dependencies and process non linear relationships in a multivariate environment. That brings me to the process flow of the ETA forecast. So for our task, we have multiple input factors like the historical train data, then geographical data, which is the name of the station, which is a station, and the distance remaining from destination. Then calendar data, that would be which day of the week is it, or which time of the day is it, because peak and off peak hours can affect the delay of freight trains. Then there's weather data, which is temperature, precipitation, snow depth, air pressure, etc. So all of these data is merged together and mapped. Um, then missing values were implemented and they were transformed into a format which would be acceptable by the LSTM model, and then they predict the delays at the destination. So this is an example of how the prediction looks like. There is a train ID which uniquely identifies a route. A route can have multiple journeys within it, which is identified uniquely by journey. Then the delay is the estimated delay at the destination, and location would be the latest known location of the train. Let me give you some insights about the data we used for our task. Uh, yeah, so the freight trains that originate within Germany and travel to Nuremberg Hafen were considered for our test. And the data was collected for a period of 1.5 years from April 2022 to December 2023. There were around 30 origins within Germany to Nuremberg Hafen, and 2875 journeys were considered um, for our topic. Uh, the left graph shows the percentage of trains that originate from different German states, and we can see that Hamburg has the highest, followed by Niedersachsen and Bremen. There are very few trains originating from North Rhine-Westphalia and Bavaria. Then the right graph shows the average arrival delay from each of these states. Hamburg has the highest delay, uh, followed by North Rhine-Westphalia and Bremen. Niedersachsen has the lowest delay of 30 minutes, and for Bavaria, it's also quite low. The next graph shows the average arrival delay during each day of the week and during different peak and off-peak hours. The one on the top here, we can see that the delay is higher during the week and reduces during the weekend. Also, during the period of 3 p.m. to 7 p.m., the delays are the highest. 6 p.m., 6 a.m. to 10 a.m. and 3 p.m. to 7 p.m. are considered the peak hours when the rush of passenger trains is high, and due to the presence of more passenger trains, the cargo trains could be delayed because they have a lower priority than passenger trains. Then the graph at the bottom shows the total count of freight trains that are reaching Nuremberg Hafen at different times of the day in each day of the week. And here we can see that the number of trains is highest during 7 p.m. to next 5 a.m. in the morning. This graph shows the distribution of arrival delay at Nuremberg during this 1.5 years. So we can see that around 30% of the trains arrived up to 1.5 hours late, and 30% of the trains arrived 1.5 hours early. Around 20% of trains had a deviation of 1.5 to 3 hours, and the remaining 20% uh, had a delay more than 3 hours, and it can range as high as up to 20 hours. And here are the results of our forecast model. So for every journey, multiple predictions were made since the train started from its origin, and the deviation from the actual delay was calculated. For each journey, we draw a distribution with the minimum, average, and maximum deviation values. And for multiple test cases, the values are plotted as here. So if we consider the average prediction, it can be seen that in 50% of the cases, the prediction error is around 40 minutes. And in 75% of cases, the prediction error is around 60 minutes. And if we look at the worst prediction, when worst prediction would be when the deviation is highest and when the train is very far from the destination. And there, in 50% of cases, the prediction error was around 1.5 hours, and in 75% cases, the deviation was around 2.5 hours. Then our results were compared with a chosen baseline method. A very common chosen baseline method is to equate the delay at the destination to the latest known delay. And it was seen that both the models performed quite similarly, with an exception that the LSTM model had a very narrower range of errors compared to the baseline, showing that it would be reliable in case of predicting significant delays in critical situations. And that brings me to the conclusion. So with this research, we were able to learn about why ETA forecasts would be important in logistics and what potential they hold. It was possible to get an insight into the distribution of arrival delays of freight trains and how various parameters like weekdays and weekends and the peak and off-peak hours would affect such delays. It also shows that what potential ML tools hold to improve, have an improvement over the baseline methods.
All right, then thank you very much for your interesting presentation and the shared insights into the topic, Shandozi. You still have the chance to ask questions about this topic in the chat. And meanwhile, I'll have a question on my own. You said like you did this calculation and forecast for Nuremberg Hafen, and in general, I would like to know like how beneficial this forecast is for container terminals, and if it's possible to also use different destinations than Nuremberg Hafen.
Yeah. We already saw the distribution where it shows that the terminal already has a delay of around 1.5 hour deviation from actual schedule of around 1.5 hours. So in our model, it is possible to predict it on average. It can predict the delays with an error of 1 hour, and in worst case scenarios up to 2.5 hours in 75% of cases. Also, currently they do not have any information, any prior information about delays. With our model, it would be possible to have this information since the train starts from the beginning. And it seems quite that would be beneficial for them. And it could certainly be adapted to any destination or any terminals.
Yeah. All right, then thank you. And Yeah, we got one question from the audience, and basically it's about the source of data, like stating that DB Cargo sometimes doesn't even know where a train is, and how much the delay is. And here the question is, wouldn't it be possible to use data from the infrastructure providers like DBNets or Bahnverkehr? And
It would totally be possible to use the data from infrastructure network in providers if it is available. For our task, the data was collected from the RNE portal. It's a rare stands for RailNet Europe. It's an association of various infrastructure companies which provide their data and share it amongst themselves.
all right. And as we are already talking about data and inputs for the model, what other kind of information would be beneficial for the prediction of the model?
Yeah, other than that, what we used, data like presence of other passenger trains and halt signals, information about construction activities and speed limitations could certainly be very beneficial for prediction.
Okay, then thanks a lot. We had one more question in the beginning of the presentation, maybe as general information. So as all of our lectures are recorded, they all will be published on the internet afterwards. My colleague Julius shared also the link where you can find the previous videos. This video will be uploaded also in next week. And so like even if you miss one of this MIUs, you have the chance to get the information from it at a later point of time. Yeah, and that brings us already to the end of today's event. Please feel free to get in contact with Shanduzi if you have any questions about the topic today. You can see her contact details here. And we will continue with our MIU series on the 26th of July after a short summer break. And the next presentation will be held by our colleague Emin Nakil-Cholyu, and it will be about workload forecasting using Bayesian neural networks. Yeah, and one more time, I would like to say thank you for all the interest and, of course, also for the speaker. Have a great weekend and see you in the next time. Thank you.